Today we're going to learn about a modification of the simplex method for minimization problems. And first, we will need to learn how to find the transpose of a matrix. We call that A transpose, notation with the T superscript. What we do is we will write, since this has 3 rows and 2 columns, size 3 by 2, the transpose will be 2 by 3. The first column in A is 1, 3, 5, so that will become the first row in A transpose. The second column in A is 2, 4, 6, so that will become the second row in A transpose. If you had a square matrix, you would simply reflect it around the principal diagonal. Just think of making rows into columns, columns into rows. Either way to think of it will work just fine. The dual problem. This is an example of a standard minimization problem. We have on our constraints, each of them we have a greater than or equal to sign and a positive constant. So in each case, we have greater than or equal to a positive constant, and we are minimizing instead of maximizing. These are the types of problems that can be solved using the dual. What we're going to do is convert our minimization problem into a maximization problem. The simplex method only works on standard maximization problems, so we need to convert this to a standard maximization problem. The first thing we'll do is we will make a matrix A using our constraints and our objective function. And I'll put the objective function on the bottom row. So if I start with my constraints, first constraint gives me coefficients of 1, 1, and a right-hand side of 8. Second constraint, I have 1, 2, and a right-hand side of 4. That's all of my constraints. Now I move to my objective function. My coefficients of y1 and y2 are 2 and 1. So I'll put that here. And we don't have a constant on the right-hand side. We have a c that 2y1 and 1y2 is equal to. So this entry right here doesn't quite line up with the others. Some people will put a 1 here, some will put a 0, some will put an asterisk. It doesn't matter. We'll still be able to do it. Now from this we form the transpose. So rows become columns, columns become rows. So my first row becomes the column 1, 1, 8. My second row of A becomes the second column, so 1, 2, 4. And then my third row becomes the third column, 2, 1, and I'm using an asterisk, but it turns out it doesn't really matter what we have in that position, because we're going to figure out how to handle that when we write the dual problem. Okay, from the transpose, we're going to write a new linear programming problem with new variables. So here's my transpose. Okay, and I've rewritten it so that it's easy to see where these new inequalities in objective function are coming from. So from the first row, I write an inequality. It's very important here that you use new variables. Before we had y1 and y2, so here I'm going to use x1 and x2. Do not use the same variables that you had in your original problem. Choose something different. So that's from my first row. Notice I've rewritten this as a less than or equal to 2. So just right across, use that to create your inequality. Here's my second row. 1x1 plus 2x2 less than or equal to 1. Now, my third row is going to correspond to the objective function, my new objective function. So I'm going to use the 8 and the 4 as coefficients. So I have 8x1 plus 4x2 equals, okay, so here we need to come up with a new letter. In our previous original problem, we had C. We were minimizing C, so we are going to call this anything else. You can call it P or Z or W. It doesn't matter. Just do not use the same letter that you had for your original objective function that was a minimization. So our transpose simply helped us to rewrite this. And now you see why it didn't really matter what I put in that spot for the asterisk. I just need to remember to put a new variable there for my objective function variable. From this, we are going to write our dual problem, which will be a standard maximization problem. So we are going to maximize z equals 8x1 plus 4x2 subject to x1 plus x2 less than or equal to 2, x1 plus 2x2 less than or equal to 1, and x1, x2 greater than or equal to 0, my non-negative constraints. This is a standard maximization problem. This is our dual problem. This problem can be solved with simplex, and you already know how to do that. So once we solve this with simplex, then our only goal will be to determine from that solution that we found with simplex what the solution to the original problem is, which is not the same as this. To do that, we're going to use something called the theorem of duality. What this says is that the objective function w of a minimizing linear programming problem takes on a minimum value if and only if the objective function z, different letter, of the corresponding dual maximizing problem takes on a maximum. The maximum of z is equal to the minimum of w. So what this says is that if the maximization problem has a solution, the minimization problem will also have a solution, and that the max of the dual problem will be exactly the same as the minimum of the original problem. Of course, we will also have to figure out, the dual problem tells us, the theorem of duality tells us that the maximum of the dual is the minimum of the original. It doesn't tell us what values of the decision variables help us to reach that minimum, but we are going to learn how to do that also. And what will help us to do that is when we solve the maximization problem, the dual, with simplex, instead of using S1, S2, S3, etc. for slack variables, we are going to use the variables from the original minimization problem. Remember, we are very careful to use different letters for both problems. Turns out that that will help us to read the values of the original variables from the bottom row. Okay. So, remember, here are our constraints. So for this first one, we are going to add the slack variables. So x1 plus x2 plus my slack variable. Instead of using s1, I will use y1 because that is the variable from the original problem. But it is still serving the purpose of a slack variable and will be treated exactly like one. Second constraint, x1 plus x2. Here's my second slack variable, y2, equals 1. So those are both slack variables. And now here I had 8x1 plus 4x2 is equal to z. So now I am going to subtract those over to the other side, and so I will have negative 8x1 negative 4x2 plus z equals 0. And we use this to write our initial simplex tableau. And I'm going to label my variables across the top. So I have x1, x2, y1, y2, z, and my right hand side. Okay, this is my initial simplex tableau. Okay, remember what we do here. We look for the most negative on the bottom row, and we choose that for our pivot column. And then we go off to the side and we calculate quotients. Here we have 2 over 1, which is 2. Second row we have 1 over 1, which is 1. We don't do it for the bottom row. So then we choose the smallest there, which will of course be this top row. Sorry, that's not the smallest. The smallest will be the second row. 1 is definitely smaller than 2. And so here is my pivot element. So what I want to do is I do row operations to get a 1 in that position, and then zeros elsewhere in the column. And I'll go ahead and write the row operations here. We would do to get a 0 in this first position. Sorry. Okay, we'll do negative 1 row 2 plus row 1 into row 1. And we'll do positive 8 row 2 plus row 3 into row 3. So that will give us this tableau. Okay, and so here we see that there are no more negatives on the bottom row. And so that tells me that we are at the optimum. Which is the maximum, right? Because this was a standard maximization problem that we set out to solve. Okay, so now we need to write down the solution to the dual problem. Keep in mind, this is not the same as the solution to the original. Okay, so what is our solution to the dual problem? Well, what are our variables in the dual problem? x1 and x2 and my objective function z. Okay, so my x1 is 1, my x2 is 0. Remember, the columns that do not look like columns out of an identity matrix, the columns with junk in them, are set equal to 0. And what about my z? My z is 8. And we should note that my slack variables, the amount of slack in the constraints in the dual problem, are y1 equals 1 and y2 equals 0, junk in the column again. This is the amount of slack in those constraints in the dual problem. Now, let's write the solution to the original problem. That means we need values for y1 and y2. Here is how we get them. y1 and y2, which are serving as slack variables in the dual problem. The reason we did that is because it turns out the values of y1 and y2 in the original will show up on the bottom row. And so it will be very handy that we use those for our slack variables. Here's where they come from. Right here. Remember y1 and y2, yes, they are serving as slack variables in the dual. And as slack variables in the dual, here are their values. y1 equals 1, y2 equals 0. Okay, but different purpose in the original. In the original, there are decision variables. And y1 is 0, and y2 is 8. See how those came from the bottom row? Now we need to write the value of the objective function. Our theorem of duality said that the maximum z in the dual would be the same as the minimum of the original. So our objective function variable in the original problem is c. So our c is also 8 from here. Okay, so this is the solution to the original problem. So we can say the minimum is c equals 8, occurring when y1 is equal to 0 and y2 is equal to 8.